guys ever watched the movie Terminators? I will be back. And I'm back again. I might be back again later in the semester. And in today's lecture, there are two topics. The first one, I'm going to talk about linked lists, continuing on what Shona has been discussing last week. My lecture will focus on the implementation bit of the linked lists. After that, I'll talk about assignment 2. All right. So in this lecture, I just have to restart a little bit, right? So in this lecture, there are two topics. One, I'm going to talk about linked lists. I'll focus on the implementation bit of linked lists. Then I'm going to talk about assignment 2. You're right, I haven't really released assignment 2 yet. I finished drafting it, and it's now with our tutors to proofread it. But while we're waiting for them, I just wanted to take this opportunity to give you a little bit of sneak peek of the assignment 2. And when this lecture recording is going to be released, assignment 2 will also going to be released probably over this weekend. So that's about the logistics. Let's dive into linked lists. So I haven't really bring all those cables and sockets and connect all these different nodes, but I did plot a little example of a linked list using, again, my favorite software, Microsoft Excel sheet. So a linked list is like this. You create small packages and all around, and you connect these different small packages. And every package, we call them a node. Now, the special things about this little package is that typically there are two fields. One of the components, well, every field, or two fields or two components. One of the components, we call it a data field. And the other component, we will call it a sort of pointer field that points to the next package. Now, by using this pointer field to keep pointing to the next package, next package is like connecting the sockets with different sort of PowerPoints. We created a structure called a linked list. And it's linked through all these pointers or the sockets. And it's a list because it's a sequential linear structure. That's a linked list. Now, how do you build, starting from a linked list that has only one sort of little package, one node, into a full-fledged linked list with so many different nodes? How do you write a code to implement that? That's the goal of today's lecture. Now, to help us sort of illustrate this concept, we don't want to sort of just deliver the code in really, really dry, and I'll just give you the code and say, well, this line of code does this line of code does that. I'm trying to sort of give us a specific sort of problem background. We're trying to solve a problem, and in the process, we build up a linked list. And this problem that we are going to solve is to find out all the prime numbers up to a given number, for example, 10. So, for all the integers, all the prime numbers up to 10 will be, we will have 2, we have 3, we have 5, 7, and there are 4 prime numbers. Now, if I give a number n, which is 1 million, how many prime numbers do you think are there? You don't know, and I don't know either, to be honest. And because of that, I don't want to create an array that holds 1 million numbers. Obviously, if I create an array that holds 1 million numbers, that's enough to host all the prime numbers within the range, right? Because we cannot have 1 million prime numbers within 1 to 1 million. It's impossible. It must be substantially smaller than that. So instead of creating an array to store all those prime numbers, I'm going to create one more package to store one more prime number that I found, and we keep creating and creating until we fetch all the prime numbers from 1 to 1 million. And that's our goal, right? So we sort of created a little bit of a skeleton already. So we say, well, our dear users, please tell me what really is this number that you want to find. Is it from 1 to 1 million, or 1 to 10, or 1 to 100? So n here is the upper bound that we want to find the prime number up to. And you would probably know it already. To find prime numbers up to this number, and what we're going to do, we'll just say, well, let's start from, we know integer 2 is a prime number. Let's start from 2, and we keep testing every number, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we keep testing and testing and keep testing. Whenever we've got a prime number, we store it. That's the idea. But the problem is, where and how do we store all those prime numbers? And that's where the linked list kicks in. Now, to use a linked list, we keep talking, we need this package or this node. But how do we create a node? Most straightforwardly, this would be what you might be thinking of to do. So if you have really sort of put your heart into Shannon's lecture about structures, you should know this is the way to create a structure or a node. And that looks like having two fields, as we just said, have a data field. And this data t here is just a type def thing that we represent an int. So you can just put this as an int that will work just fine. We use a data underscore t type instead to make this code looks a bit more generic. It doesn't have to be an int package. It could be a package to store double, could be a package to store student records, could be a package to store whatever that you can think of. So we use a data t type in here. And this is called a data field. And then we have a pointer field to point to the next node. And most naturally, this pointer will also need to have a type. But what would be the type then? You might think that, well, we're going to call this package type the node type. Then the pointer should point to the next node, and it should also have a node type as well. And this is quite natural. We are going to create a package, a node like this, right? Can we all agree on this? The only issue is, if you're trying to compile this piece of code, the compiler is going to complain. And let's see what it will complain. It's going to complain saying that it doesn't really understand what do you mean by node underscore t. Let's look at what's happening in the code. So when the compiler trying to sort of translate this piece of code into a machine understandable code, what it does is it's going to read starting from the first line, second line, and it's trying to sort of translate each line into a machine understandable code. Now, when it touches this line, it finds that there's a keyword that says, there's a word that says no underscore t. But no underscore t is not a system-defined type. It's not like an int or a double or anything. So it doesn't understand what it is. For us, we know that no underscore t actually means a struct type called no underscore t. But unfortunately, the compiler is not as smart. It always reads from top to the bottom. When it reads this line, it doesn't know what no underscore t means yet. So this wouldn't work. Now, to bypass this limitation, we have to go for a slightly different way of defining a struct. So instead of using a type def, we say, well, let's create a struct. And we give the name to the struct already. Let's call this struct a struct node type. And if we do this, at the time when we hit this next pointer, it already knows what this node type is. But of course, here, let's change the name a little bit. It doesn't really matter if we call it a struct node or struct node underscore t. It's just a type name anyway. So here, just to be consistent with the slides that I'm going to show you next, let's call this struct type node. So if you define a type like this should satisfy the compiler. It will read that there's a node type declared, and here is just a pointer pointing a variable of this type. It should satisfy it. Not quite, and now it's super messy, a lot of errors. And let's clean up. Let's try to clean up the mess and try to locate where is the first line of error. So apparently this is the first error that it got catched. It says that it still doesn't understand what it means by this node type. And the issue for this is, without using the type def stuff, whenever we create a struct in this way, and whenever you use a struct type of this type, you have to accompany it with the struct keyword. You have to keep saying struct node. So now you have to always write two words to represent one type. With the previous type def style, you only need a no underscore t. It already knows that this is struct type. But with this style, you have to always say struct node, and this represents a struct. And if you're trying to do the compilation again, and again, there are still a lot of errors, but at least this this error is gone. So where was my compilation command? Can we find it now? Well, let's clean up. Is this my command, really? Oh yeah, this is my command. This is the last compilation command. And as you can see, the previous unknown error on the node is gone. Now the first error is node underscore t. That's because the later bit of code has this node underscore t type. But at least the first line of error occurs now from line 25, which is not this line anymore. So this part actually passed the compilation. So it worked. Yes? Exactly, that's what we are going for next. So now at least we have this one work, but having to say struct node in every time is cumbersome. So, well, let's type def that. So we tell the compiler saying that, well, please trust me, there's this struct type node that's coming up very soon, and let's just call it node underscore t. This way, the compiler already knows that there's this struct that's coming up, and it's going to be called node underscore t from now on. And because of that, the compiler already knows that. I don't need to write this struct node again. I just say node underscore t, and I got a pointer pointing to the next struct type variable. And this is the way that has been used in the slides. Let's try to compile this piece of code and make sure that we get it right. And suddenly, all the errors are gone. And yes?
Why do we need that semicolon after the curly bracket?
Oh, this one. You mean this one or that one?
The bottom one.
This one. Yeah, because we are creating a struct.
So it's like initialization or declaration, I guess.
Yes, it's a type declaration. It's just like before, previously you might see a struct type definition that looks like this. You're saying type def, and you create a struct. This is actually called an anonymous struct, a struct with no name. And then I'm going to give it a name, which is linked list. And I'll put a semicolon in there to end it. Yes? No and no underscore t, there's no difference. No underscore t is just a different name of node. In this case, it matters because without this type def line there, the compiler wouldn't understand what it means by node underscore t. Yeah, that's just that. But in reality, in a later example, for example, if you just want to create a linked list of this type that doesn't really need to rely on the linked list type itself to define the linked list, then it doesn't really matter which style you go for. Okay? This is just a bit of a sort of language issue. You don't have to worry about this. Nothing magical in there. This is just to satisfy the language rule of the language. So I also don't want to spend like the whole lecture to just explain why we come up with this. This is just the way to create a struct. Anyway, so far so good? Or you're still confused? If you're still confused, rewatch this bit of the lecture recording. That's the recommendation I'm going to give, and I won't spend more time on this one. Now, once we have created a struct type, the next thing we can do is actually to use this struct type to create variables, such that we can create nodes to store the prime numbers we got. And to create variables, and we'll just say, well, let's create a node, and this will be used to host a node. That's just that, all right? And obviously, we have used the node keyword previously as part of the struct type definition, so let's not reuse it just to minimize confusion. Let's just call it a new node. And we use a pointer variable to do it as a convention, because if you think about it, whenever you got a new piece of prime number you want to add to this linked list, you have to create more and more nodes. And if you want to create more and more nodes, you have to call this malloc function to sort of fetch a piece of memory to create a new node. And to fetch a piece of memory, we need to catch that piece of memory. And to catch that, we use a pointer variable called this new node pointer to catch a node. Now, beyond a pointer variable to catch a new node, we also have to have pointers to keep track of where's the starting point of the linked list. Right? You have to have that head pointer pointing to the first node. So we are also going to create pointers called the head pointer. This will point to the very beginning of the linked list. And as a convention, we also use a foot pointer to point to the last node in the linked list. And at the beginning, apparently both head and foot, they are not pointing to anywhere yet. This is how we start a linked list. And visually, looks like something like this. This head, foot, and new node pointers, each of them is a pointer. As a pointer is still a variable, so each of them will hold a piece of memory, and it has some memory address. Now, each of them will point to somewhere. At the beginning, they are not pointing to anywhere yet, because we haven't really got any node yet. So this would be the setup in the main memory of all these three pointers. The number here represents its memory address, because these are still variables. They will have a memory address. And these numbers are just some random numbers that I gave them. So that's just that. To be consistent with my Excel sheet, I'll just call this new, all right, new pointer. Now, here comes the actual meat, how to add a node and put it into a linked list. So we got a prime number. Apparently, 2 is a prime number. We got a 2. How do we add to the linked list? Apparently, we will need to create a node to host that, right? So this new node need to got a piece of memory for that. To got a piece of memory for a node, what was the command that I just said? Malloc. Very good. We got a piece of memory for the new node, right? And as a convention, because the memory malloc function will return a piece of memory, and that's just a memory address. A memory address can be used to store like that address. The memory at that particular address can be used to store anything. Here, we just tell the system that we are going to use to store a node. So we just sort of give a typecast to say that it's a node type pointer. And how do we use malloc? We have to tell the system how large is the piece of memory we want, right? So how large is the piece of memory? Apparently, the size must be the size of this struct type, right? So we'll just say size of node. And this is a typical way of using malloc. You don't have to remember that, well, for this struct type, apparently we are looking at an integer 4 bytes, and then there's a pointer is 8 bytes because I have a 64-bit machine, so 4 bytes plus 8 bytes, 12 bytes. I don't have to say here, malloc, let's allocate 12 bytes. Typically, we don't do something like that. Instead, we just use this size of sort of pseudo function to tell us what really the size of the type. We put a type in there and let the size of function to figure it out. So we got a node. So what? What next? We got a node, we got a memory. Then we need to fill in the data, right? And there are two fields. One of the fields is called the data field, and there's another field which is the next pointer. So both of them, we need to sort of fit in some data. So what to fit in? Data must apparently should be the prime number, right? I is a prime number, so we fit it in. How about the next pointer?
Memory address.
Memory address? Of what? pointer of the prime number, yeah? Now, okay, now. So look at this example. Now we got a new node, and this new node points to somewhere, and the data field is 2. This is supposed to point to the next node. This is a pointer field. But at the beginning, we don't have a next node yet. So let's just say there's nothing next yet. So put it as null, all right? Okay, we got a node. If you look at this Excel sheet, what's the issue? Comparing this Excel sheet with the other one, what's the difference? Except for that, this other sheet has a lot of numbers already. What's missing? It's not linked, right? We have this isolated node. We have to get it linked. Look at this example. This is the first node we created. After the first node created, what else should we set it up? There's a little arrow in here. We have to use a head pointer to point at it. How do we make the pointer to head pointer to point at it? We say head equals to new. Because new is a pointer that points to a node, and if we set head equals to new, then the head pointer now points to the new node. That's the way to do it. Once we say head equals to new, essentially we update this head pointer's null field, null value, to this memory address, which is 2061, which is the memory address of the new node, and set up this little arrow in here. That's what this statement does. And that's very good. And that's essentially our first sort of linked list code. Yeah?
In that case, like every time we got new prime number, we add that to a new node to item. And we said hash to the latest one. I think that will work. Where then you had to always the newest one comes first.
So you are challenging me.
Yes.
And I don't believe you. We will come back to that, all right? Let's just sort of agree on this is the way to set up a linked list. Next, once we finish that, apparently we want to print out the content, all the prime numbers that we want to find, that we have found out, right? So let's print it out. So how do we print out a linked list? Apparently, to print out a linked list, we have to use a while loop to keep going to the next and next and next, right? That's how the way to do it. So we're going to say if the head node is not empty, apparently the head node is pointing to somewhere, let's print out the content at the head node. And the head node content would be apparently still the data field. That part, so far we can agree on this, right? And once we are done with the head node, let's move on to the next. This is the way to print out. Apparently there's some details that we need to figure out still, but let's just use a very simple version of the printout, and let's observe the behaviors of the program. There's something that we haven't, print, a typo there. There's a warning, we haven't used the foot pointer yet, but don't worry about it. We can just power through and power forward, and I'm just trying to run this one. It's waiting for me to enter a number. Let's try 10. Oh, we got a 7. What's happening? We are supposed to have 2, 3, 5, 7, and we got 7. That's good. And the reason why we missed 2, 3, 5, well, apparently your challenge is correct. I did miss something. So what did we miss? Apparently we missed all the previous ones. Why did we miss all those previous ones? The reason for that is whenever we create a new node, we use the head pointer to point to the new node. So when we create 3, head point to, when we create 2, we point to 2. When we create 3, head points to 3. When we create 5, head points to 5. When we create 7, head points to 7. All the previous ones are gone. And that's not great. We have to fix that. So there must be some two different cases that we have to cater for them. We need to do a bit of testing. If the head is null, meaning that this is now the first node. The first node, this setup is all good. Just as an additional step, we also made the foot to be the new node as well. So first and last one both point to this new node. Now, if the head is not null, that means there's a node that has been created already. In that case, if there's some node that has been created already, that's pretty much this scenario then. We have a linked list that has been partially created. Now I got a new node. Apparently, I have an example that have created quite a few nodes already, right? Suppose now we are at this moment. We have figured out prime numbers up to 17. And now the next one we found is 19, and we created a node to store 19. The next thing we want to do is actually we want to add 19 to the end. But how do we make a connection? Apparently, we want to set this now to 30, 20, right? That would be the goal. If we set this null pointer of the last node to be the memory address of the new node, then the last node will connect to this new node. How do we set that? We send say else, and apparently we need the last node, assuming that we have that last node. And we're going to say that last node's next to be, you can stay, to be new, right? What I'm trying to say is, if you want to connect this new node to the end of the linked list, apparently the last node's next pointer here needs to be updated to be the memory address of this one. And this is the way to go. The only issue is, how do we get to the last node? It's the foot, right? We have this foot pointer to point to the end. There's still one thing missing, though. After we finish this one, the foot is not the last one anymore. We have to update it. So let's make the new node that we just created, make it to be our new foot. And that's the way to go. Hopefully this time it will work. Try 10 again. Does work. Oh, actually this percentage sign, I think it's a setting of my code. I let it set it such that to show that's the end. I don't believe there's anything else that's erroneous with our code. I believe that's it. Or did you guys see anything?
I get it all the time.
Yeah, so, yeah, probably it's the output setting somewhere. Yeah, so it should be fine then. Yeah. And that's pretty much it. Now, if I do this, there's still one more thing. Like, I can keep doing and keep printing. And I set up the linked list already. I can print out the linked list. After I finish, remember, after malloc statements, we have to free the linked list as well, right? So next, our goal would be to free the linked list. And to free the linked list, apparently we will do the same stuff. So for every node, I'm going to print out the node, and well, I don't need to print out the node. For every node, I'm just going to free the node. And then I'm going to move to the next. And after the whole for loop, I'm going to free every node in my linked list. Now, there's a couple of issues in this implementation. First issue is the head still the head? Not really, right? Because after the while loop, we actually have moved to the end of the linked list already. And we can't just keep freeing it. So we have to actually preserve the head. So typically, when we want to go through a linked list, we don't really modify the head pointer. Instead, we say, well, let's let this new pointer to be our head pointer. And let's use this new pointer to keep moving to the next. And that's the way to go. Yeah?
Why don't we just free the library right after we print it out?
Oh, definitely. Right after we print it out, we just free it. That's completely fine. In this particular small example, that's completely fine. But in reality, usually you don't free a node right after you've done some modification to it. You still want to use it for other things. And only after you finish everything and all done, you free it. So that's the reason why I've separate the printout and the freeing into 2 stages. So that's the way to go, yes?
When you frame it, you just frame the pointer to the struct, not the actual struct itself.
Actually, it's freeing the struct, not really the pointer.
So by passing the free function, the pointer to the struct, that deallocates the entire struct.
That piece of memory holding the struct got freed.
Okay. Yeah.
And when you talk about freeing a piece of memory, it's not like you cut the piece of memory out. It's not like that. When you free a piece of memory, all that you do is just to tell the system that this piece of memory, I'm done with it. You can reuse it for other purposes. And when we talk about memory allocation, it's also not like it cuts a piece of memory and give it to you. It's not like that. It's still the same long tape of memory. And when you allocate a piece of memory, there's a little table called memory allocation table. The operating system keeps basically do a bit of bookkeeping, keeps a table that says, all right, for memory address starting from 2000, and there are 20 bytes, that has now been allocated to program A, and there's a record in there. When it's freed, all that the operating system does is just to cut through that record, wipe out that record. That's all that it does. And because of that, after we free this piece of memory, your content is actually still there. The structural content is still there. Only when another program that comes into it and read it and is trying to override it, then your content is wiped out. But that's actually dangerous. It's not to our purpose, right? So what we really want to do is, after we free this piece of memory, we want to say, let's forget about it. Even though our content is still there, may still be there, but I don't want to access it anymore. So that's the way to go. But if we do something like this, we can't go to the next node again. So what we need to do again, we have to use something to help us. We're going to say, well, head is not now. Let new to catch the current head. And let's move to the next node. And now we are ready to free the previous head node. And we're going to set it to now. And in case this one, whether it's set or not, doesn't really matter, because in the next iteration, it's going to be updated anyway. So I don't need to do anything about this. But in the end, I still need to sort of set the final head pointer to be now. And similarly, I'm going to also clean up the foot pointer and the new pointer. And everything now points to now. I wouldn't be able to accidentally access the previous piece of memory allocated to these pointers. That's the way it could go. So far, so good. That's how you add things to the end of a linked list, how you sort of go through the items in a linked list, and how to sort of free the memory of the linked list. Now, that's probably really the most important sort of technical point that we want to cover. The next one we're going to say is, we can't just write all the content in one main function, right? We have to cut it into functions. How do we cut it into functions? To cut it into functions, apparently we need to keep passing this new and head and foot pointers into all the functions, and I can sort of cut this piece of code into a function call. That's all that, and that's all fine. It's just that I have to pass so many different pointers. To reduce the complexity of passing all these pointers, we create an additional structure called a linked list structure. And this linked list structure is just a package of 2 pointers, the head and the foot pointer, such that whenever I need to use a linked list, I'll just pass the whole package of a linked list into a function call. And this linked list will have 2 pointers already. And to do that, this is essentially the final version of the example. I'm going to create a linked list. And for this linked list, I'm going to create in a pointer way. Why do I want to create into a pointer way? Remember, I want to pass this linked list into different function calls to make modifications. And when we pass a struct into a function call, we say that it's actually quite expensive because a struct, whenever you pass a struct into a function call, it needs to create a copy of the struct. It's actually quite expensive. If we pass a pointer into a function call, it's always just copying the pointer, and the pointer is just 8 bytes. And that's a lot cheaper. So that's the reason why I want to keep passing a pointer. And I'm going to create a function called create empty list to initialize a pointer. This is essentially doing what I just did to set a head and foot pointer to be null. And that's what this create empty list function is doing. Setting the head and foot pointers to be null. And this time, only that, because this list is now a struct type pointer, we have to access one of these components, the head component and foot component. And to access this head component, we use this arrow operator rather than a dot. And head and foot, both set them to be null. And before that, I also need to sort of malloc a piece of memory for the linked list structure itself. Remember, the linked list structure itself is a struct and has two fields. One is the head pointer, the other is the foot pointer. And these two pointers itself, they are variables. And for variables, we have to create sort of space for them. So we first malloc, and we are mallocing the struct type of the linked list type. And one here means I only need one linked list. That's just what it does. Create a piece of memory. The good news about this memory that got allocated in a function is that it will not be destroyed after the function call. It will only be destroyed when we call free. So it's not like an array. If you create an array inside the function, you can't return the array because after the function call, the array will be destroyed. But for a malloc piece of memory, we can keep using it. That's the reason why we malloc a list. We set up its head and foot pointers, and we can return the list. There's an assert function call to make sure that this memory allocation has been successful. This is a standard procedure. Whenever you call a malloc function, you always sort of follow it with an assert statement to make sure that the memory allocation has been successful. Because there's no guarantee that you always got your piece of memory allocated. Actually, especially if you're using a Windows PC, I'm not saying that MacBook is much better, but it's just a general observation, especially in sort of maybe my generation of computers, maybe 10 years ago, when the memory sort of management of the operating system is not so great. After you start up your computer and you keep it running for a while, you observe that the computer becomes slower and slower and slower. But if you reboot it, the computer becomes a bit faster again. What's going on? What's going on is, for all those programs that you start after you started your machine, they keep calling the malloc function to fetch more memory. And they keep fetching and keep fetching and keep fetching. At some point, there's usually no more memory left. And they have to keep waiting for the next piece of memory that is made available. And that keep waiting part is the part, one of the reasons that makes your computer running slower and slower. But if you reboot your machine, then the memory allocation table got wiped out. And everything got started over again. And that's what's going on. And that's the reason why we say you have always to assert to make sure that that piece of memory got allocated as intended. Right? So that's the piece of memory allocation. So far, so good. So we allocate a piece of memory for the linked list. After that, we can use it to add nodes into the linked list. And to add nodes into the linked list, we have a few different functions. In here, we are always adding nodes to the end, right? We are always adding nodes to the end. We call that insert at foot. And to insert something into a linked list, essentially it's just this statement. We want to insert at foot, and this is the linked list we want to insert into, and this is the data field that the new data value they will insert into the linked list. So we call this insert at foot function. And this insert at foot function is basically just a duplicate of that piece of code that I just created. We want to sort of malloc for a new node, and we want to test whether this new node has been malloc successfully. This is essentially the assert statement in an expanded way. The previous assert statement that we're shown in here, essentially, that's what it does. Here, I can replace this with assert new. That will serve the same purpose. And then the new item got added to the data field, and then it starts with a null pointer at the end. And if the head node is null, means that we don't have the content yet. We set both head and foot to the new node. Otherwise, only the foot next will be the new node, and the foot the new node becomes new foot. This is essentially a repeat of the piece of code that I just delivered anyway, so I won't repeat this one again. So that's the way to go. We insert at foot. And similarly, this sort of printing and freeing operations, we can also replace them with a function call. The print function call, this is a standard procedure to go through every node and do some operation on every node. Here, the operation we're doing is just to print out, but you can modify this to sort of operate on list or modify list. You can, in fact, in assignment 2, you're going to pretty much sort of do something to modify this function for the assignment. And all this function does is just that making sure that while the list has some content in there, there's a little bit of content tracking, safeguard tracking in here. If there's a content, we create a new node that keeps track of the looping. So we doesn't really change the head node. We only change the new node. The head node stays at the head, at the initial node of the linked list. And finally, we have a function to sort of release the memory. We say free list. And free list basically is just doing what this print list does. Go through every node. Go through every node and free every node. In the end, there's only one more thing. We have also need to free the list pointer as well. Because for this linked list, we malloc a piece of memory to store the linked list structure, right? So we also have to free it. You might also need to remember, after freeing a pointer, we set it to be null. The only issue, though, is we can't do it in here. If we do it in here, it wouldn't work. Remember, what happens inside a function stays inside a function. If you change the linked list and use it to point to somewhere else, it wouldn't have an impact outside of the main function. We have to set it to be null back in the main function. Otherwise, even if the mylist is pointing to, even if you have freed it, you have set it to be pointing null, but back in the main function is still pointing to the same previous linked list piece of memory. So the setting back to null has to happen in the main function. So far, so good. And that's linked list. Now, we can take this even a step further. I can cut all those linked list functions and store them into a separate program, and we call it a listops.c. And this listops.c is a package of linked list implementation. It contains the structure definition. It contains a few functions, including creating an empty list and testing whether a list is empty or not. And to test that, essentially just test whether the head pointer is null or not. If it's not null, that means there's something in the linked list. If it's null, there's nothing in the linked list. And you can free the list. This is exactly the same as what I just showed, except that it's using a different sort of pointer variable name, using cur rather than new. And there's this insert and foot function, which again is just exactly the same as the one that I just showed you. And additionally, there's a few functions, including insert at head, which is just like previously we say, after we've got this node, created a new node, let's add it to end. But on the contrary, we can also add this node to the front as well, and that's insert at head. And I strongly encourage you to play with this bit of code a little bit after class. When you use linked list, when you modify a linked list, the most important bit is how do you update, how and when do you update all these pointers? Whenever you need to modify, like insert a node into somewhere in a linked list, apparently it will impact the pointer of this previous node, and potentially the pointer of this next node, and the pointer at the node that you want to insert it. And the order that you modify these pointers has a heavy impact in the result. If you are modifying these pointers not in the right moment, you might lose the whole linked list, or at least part of the list after the point where you want to insert it. And that has serious consequence in terms of how the program runs outcome. So be careful, and you have to play with it. I show you how to modify the end, which pointer should go first. In this case, I'll show you if you want to insert. We show you that if you want to insert a foot, you have to update the foot's next pointer first, and then you update the foot pointer itself. But if you want to insert at the head, you might want to change the head pointer, and the head pointer might not, and the head's next pointer, and also the new pointer. You might want to change all those. But which one got changed first is that's very important, and you have to play with the code to understand what's going on. All right? There's also another function called getHead. This is just to get the head node, the data at the head node specifically. And there's also getTail. Importantly, the getTail function is not to getTail is a bit different from getHead. GetFoot. If you have a function called getFoot, typically that will give you the foot pointer. But getTail is to get the linked list except for the foot, except for the head pointer, except for the head node. So a linked list has a head node. The rest of it is the tail. It's not like the last one. It's not the last one node is the tail. The first node is the head node. The rest of it is the tail. So that's what's going on in here. And what it does is that it updates the head node to be the next node pointing to by the head node, basically the second node in the linked list. If you update the head node to point to the second node in the linked list, you lose the original head node, and the rest of the remaining of the list is just a tail. That's what the getTail function is doing. There's also an example called list.eg.c that shows you how to call these library functions, or not really library, a package that we create on our own for the linked list. And it shows you an example how to call all those functions, and you should play with this example. And all this example code, you can find it in the lecture slides that we showed on our website, lecture slides set 7. If you go to this linked list section of the slides and you go to the end, you got 2 links linking to the 2 example code that I just showed you. So far, so good. Before we take a break, let me just quickly go over these slides, make sure that we've covered everything. And after the break, we will talk about assignment 2. So this is how we create the, This slide shows the struct definition to create a node, and this one shows you the struct definition to create a linked list that we just show you in the code anyway. So I won't repeat it again. Now this slide is interesting. It shows you if you have a linked list, this is the starting setup. You don't have anything in the linked list yet, both head and foot pointing to nothing. If you create a linked list, if you create a node, then you need to use the head pointer and the foot pointer to point to this new node, as we just shown you, the inserting a point number 2 case. After that, this third case shows you how to add a node to the end, and you need to really work on these pointers. How to update, so actually this is inserting at the head rather than at the foot. So originally this is a setup, you have one node, and then you want to insert a node before the foot node. Now to insert this new node before the foot node, what you need to do is this new node's next pointer need to be set up to point to the previous foot node, and then the original head node can now point to this new node. This is the way to do it. If you set up this pointer in here, if you connect this pointer first, then it's dangerous. You might lose this node. Because originally the head node points to that. If you update this head pointer to point to this new node, there's no pointer to point to the last node. Or you might argue that, well, in this case, the foot node pointer can still point to that. But this is just a special case with only one node, where this one node got 2 pointers. If you think about it in a different case, where there are another node in here, then the foot node pointer will point to the last node. If you insert this new node in here, then there's no pointer to point to the second node anymore. So the pointer to point to the second node must be set up first before you update the head node pointer to point to this new node. This is the key challenge. This is a key challenge when you're trying to modify the nodes in a linked list. What's the order to update the pointers? And this one is just to insert a node at the foot, and this one we have shown you already, so I won't repeat it. a few sort of standard sort of template function that we do to access linked list. This is the print list function essentially, except that it's not to print, but to do some process. And our process that we've shown is just to print that data. This is the insert at head function. The two key statements are in here. You have to set up the new node's next pointer to point to the original head first. And then you update the head to the new node. So what I'm trying to say is you have to update this pointer to point to here first, and then you set up this pointer. This is the key bit. In getTag, we already shown you already, so I will skip. And this is the list example code that we just shown. Shannon also talked about this queue and stack structures. A queue is just a structure that you always insert at the front, well, insert at the end. A queue is insert at the end, you sort of remove at the front. That's a queue, right? First in, first out. A stack is first in, last out. So you always insert and remove on the same end. That's a stack, right? You should really try to use that package of linked list to implement, trying to implement a queue and a stack. And actually, that's not so complex because all that you do is just to throw away some of the functions in the linked list, and you got a queue or got a stack. Why? Because for a linked list, you can insert at the front, you can delete at the front, you can insert at the foot, and you can delete at the foot. But for the queue and for the stack, you can only insert at one point and remove on also one point. So you just remove one of the insert functions and remove one of the XX functions from a linked list, you got a stack and you got a queue. That's the idea. Make sense? And that's linked list. Anything else? Otherwise, we will take a 5 minutes break and we will come back at 2:50. Okay, take a break and we'll start again at 2:50. Hopefully, we will just need like about 30 minutes to cover the assignment 2, and as I said, you get a few minutes early to take a coffee break. So assignment 2. Now, assignment 1 is due this week, and we're going to release assignment 2 in the coming couple of days, probably over the weekend. Now, in assignment 1, or in the subject, we cover binary search and searching for numbers. Then assignment 1, we extend the search to multi-dimensional numbers. We haven't covered string searching yet, even though in the subject we have talked about like KMP, all those complex algorithms that Shannon spent quite a bit of time to sort of come up with a good example and then the lecture recording. Now, in assignment 2, we're going to try to put string searching skills into test. Now, the setup would be like this. We're trying to sort of follow the setup of assignment 1 such that we don't have to sort of switch context. We still consider POI searches to look for places of interest. The exception, though, is that in assignment 1, we assume that, well, we already know that all the POIs we gave you are sort of cafes. You just want to find a cafe near you. Now, in assignment 2 is that we want to sort of expand the search, not just for cafes. What if I want to find shops, restaurants, like movie theater, university for no reason? How do we do it? You're going to be given a set of input that looks like this. These are still the point of interest, the POIs, and each POI now has some sort of categories, some strings that comes with it that represent the categories. For example, here the first one is a location that probably is a petrol station that comes with petrol. There's an ATM machine there. There's also car wash services. Another one that's just an ATM service. Another one that's more like a shopping mall with some shops, supermarket, again ATM machine, and then Coles and Woolworths, and so on and so forth. So we give every POI a keyword. We call this a category. Now the search also comes with, again, a range like before. These are the bounds of the search range. And then there's a particular category of POI that we want to look for. For example, the first query wants to look for cinema. Second one wants to look for like ATM. Third one petrol station, first one supermarket, and the last one wants to look for cafes like before. So that's the setup. And now the search will go like, well, you can probably imagine, to do this search, you will still repeat what we have done before to use the location to filter out the things that are not in the area of interest. After we find out the POIs in the search range, we want to try to match the keywords. That's one way to do it. But it may not be the most efficient way. And we want to do it, maybe we can improve the efficiency by doing a reverse way. So we will first go through the sort of POIs and try to match, for example, do you have a cinema keyword? 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 Oh, here we got one that has a cinema keyword. Then I check, are you in my search range? So that's the other way. But either way, it sounds like a lot of search. Can we do a bit better? And this assignment aims to do a bit better than that. So first stage would be just to read all the POIs, essentially to read the first section of the input. Read all the POIs, and we ask you to print out how many POIs did you read? Apparently in this example, 12. And we want to ask you which is the POI that has the large number of categories. In this case, the third POI, POI ID 2, has the most sort of categories, like 5 category keywords. That's first stage. Second stage would be just to read and process the queries like what I just described, just to go through the queries in a straightforward way. For every query, we go through all the POIs and say, are you in the range? 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 If you're in the range, do you match my keyword? Do you match my keyword? Do you match my keyword? That's stage 2. Stage 3, now we bring up the challenge. In this stage 3, we want to try to use the keyword the category word to help us to streamline the query processing a bit. And the idea to do that is, let's first fetch out all the unique keywords. In this case, apparently some of the keywords are shared between different POIs. For example, there's quite a few POIs that come with an ATM machine. So we look out which are the unique category keywords. And apparently, out of this large set of category keywords, we find out that there are a total of these 15 unique ones. So after we got the unique ones, what we are going to do is that for each unique POI category, we attach it to all the POIs that has this keyword. For example, we figure out that for this ATM category, it comes with POI 0, 1, 2, 8, 9, 10, 11. Let's see. For ATM, it comes with 0. ATM comes with POI 1, and then 2. Nothing more in here. And then POI A has 8 has ATM, and 9 has ATM, and 10 and 11 they all have ATMs. So for each of these unique POI categories, we attach the list of POIs that has that category. And we repeat this for all these unique POIs categories. Now, once we have attached that to that, the query processing will be simplified. All that we need to do is just to go through this list of unique categories. For a query that looks for cinema, I'll just say, all right, you look for cinema. This would be the list of POI that might be relevant. And then I'm just need to check whether these POIs are in the query range. And that's the last stage. There's a bit of an additional processing about last stage. Previously, these are all these unique categories in the order that they appear in the input. For example, petrol is the first keyword that appear in the input, and then ATM, then car wash. So in the order of the input. So in the last stage, we also ask you to reorder them to sort these keywords, these category words alphabetically in dictionary order. What's the benefit of doing this? Once we sort it in this order, again, binary search kicks in. We can quickly locate which is the keyword that matches a search keyword. And then we just need to go through the list of the items, the POIs in here to answer the query. How fast can this be? What would be the time complexity? And that's the last question of the assignment. Tell me, what's the time complexity to do query processing using this structure? This is actually called inverted index. And it enables a faster query processing. And we ask you to tell me what would be the time complexity to do a query using this linked list. We also ask you to analyze using the straightforward query processing technique that we just go through everything and do the matching. What's the time complexity? We ask you to do a bit of comparison. That's assignment 2. Excited? Can't wait for it. It's coming in a couple of days. Now, we are also going to give you sample test cases like in assignment 1. We are also going to give you a skeleton code, but this time the skeleton code is going to be a bit simpler, not like the previous one, which we pretty much give you half of the assignment already. The assignment 2, you need to do a bit of more coding or more designs, but I assure you, you're going to be getting enough support. You got hints all over the assignment, except that we don't give you direct code. You have to sort of figure it out. You're also going to be given a marking rubric, and here, let me show you the marking rubric. It's pretty much like the previous one. There's only one section that has a bit of difference. In particular, the structure and approach. We ask you to do a bit of additional stuff. One thing we ask you to do is to try to use type def and use structs. In assignment 1, we didn't ask you to do it, but now is the time to sort of try it out. The other one, because you can use structs, that means you can package you can package things together and pass it into functions using structs. And because of that, you can actually reduce the number of function arguments. So we also ask you to limit that within 6 arguments for every function call. We also want you to try out the linked list code that we just presented in today's lecture. So if you're not using it, there's a bit of deduction in there. We also ask you to try to do a bit of time complexity analysis, and that's just it. So these ones in bold are the main things that differs in the 2 assignments in terms of the evaluation and sort of assessment. Well, looks like I only need 10 minutes to cover assignment 2. Any questions? Let's see. Still there? Great. Yeah. Yes?
Do you mind showing stage 4 again?
Definitely. Stage 4.
So if, for example, we're looking for an ATM
Yeah.
in like some boundaries,
Yeah.
are we gonna have to write an algorithm to like, do we just do a linear search over those IDs, or
Yeah. The good news is for stage 4, we only ask you to construct this structure. We actually didn't ask you to deliver the actual query algorithm based on the structure. We actually gave you the query algorithm, and you can analyze this algorithm. What would be the time cost if you have this structure and you want to run a query on it? And you can design it. You can sort of talk about your design, exactly how you want to do it. Do you want to do a linear search, or do you want to do that smart search we designed in assignment 1? These are, yes, sorted based on ID. Yeah. Yes? Yes, due date 21st of May. So again, 2 weeks time. Anything else? If not, maybe I'm just trying to sort of spend a bit more time in the lecture such that Shannon don't think that I'm trying to be lazy and don't deliver 2 full lectures. Yeah. Yeah. Yeah, don't tell him, right? Yeah. I'm just trying to quickly also show you the skeleton code that is going to get. There might still be slight changes after your tutors proofread, and if they found any mistake, I'm going to change this. But this is, in general, what you're going to get in the skeleton code. We gave you some structs templates already. You need to fill in the contents. These are structures that you want to create, and if you want, you can create more as well. We also give you that piece of linked list code that you can use already, and you just call it to manage the. We ask you to use a linked list to manage the queries, because this time we don't tell you that there's up to 5 queries. It could be 5, it could be 500, but in reality we won't really test you with so many queries. But because we didn't give you the upper bound, you have to use a linked list to manage the queries, and you can use this linked list to store all those queries. You still got 4 stage functions. This time we didn't give you all those function parameters. You have to design them on your own. And we also, in the main function, we didn't give you what kind of variables you need. You have to design on your own. And we give you a very simple skeleton in the main function, calling the 4-stage functions that essentially doesn't do anything yet. Just print out the stage headings like before. So it's not really much. This time you have to actually deliver the code on your own. We only gave you the linked list functions that you might need to use, but if you want, you can sort of write more. And at the end, don't forget to write the time complexity analysis. You don't have to, for the create algorithm of stage 4, you actually don't need to code the actual algorithm, but you need to be able to analyze if we design such an algorithm, what would be the time that it's going to cost. All right. Anything else? Any final question? No? All good? And it goes as our second lecture. Don't tell Shannon that we finished so early. See you next time.